started. So first of all, I'd like to welcome all of you to the workshop on the Perturbo-code. We are delighted to have you here, both those of you who have made it here to Caltech for the in-person event, and those of you who joined on Zoom. I'm Marco Bernardi, and first I will give a brief introduction and overview, and I will go over the schedule for the next 2 days for this workshop. So this project started a few years ago in my group at Caltech, where we basically wanted to develop efficient computational tools, initially to compute electron-phonon interactions and the associated transport properties and non-equilibrium dynamics. Then over the years, the project morphed into a much broader scope set of tools and ideas, and I will cover some of that in this brief introduction. Now, joining me today is the wonderful team of students and postdocs who have made this workshop possible. The 10 people that will give talks in the workshop are showing here in this box. I also wanted to thank some of the students who couldn't make it, but particularly Jinji and Zhu, who's a former postdoc in my group and is the one that wrote the first version of the code. He's now a professor at Beijing Tech, and he couldn't make it today. Thank you. No, it's fine. It's fine. Yeah, I hope that people can hear me. Okay, so what's the plan for the next 2 days? Now, today, after my introductory talk, there will be a practice session explaining how to download and install Perturbo, how to compile it, interfacing with codes like Quantum Espresso and 2090. And also, it will go over tools to handle input and output and efficiently post-process calculations. Now, following that, we will have 3 more blocks, each one made up of 2 talks. The first one will be a theory talk, and the second will be a practice tutorial. And these talks will be 45 minutes each, with 5 to 10 minutes for Q&A. And so since we're running Zoom in webinar mode, people who want to ask questions can type them in the Q&A box, and then we will wait until the end to read and answer the questions. So I hope that you had a chance to download the workshop materials from the link that you have received in the email. And I wanted to really highlight that this workshop has been organized and basically is going to be run entirely by the students and postdocs in the group. And so this is really possible thanks to their effort to put this together. And so this is the plan for today. And then I wanted to mention that on day 2, tomorrow we will have a hands-on session where the participants, both here and on Zoom, will be able to try out some calculations assisted by the students and postdocs in the group. Okay, so broadly speaking, Perturbo provides a wide range of tools to study electron interactions and dynamics from first principles. The current version, which is version 2, can compute the interactions between electrons and phonons and electron and defects in materials. I want to say with up to about 50 to 100 atoms in the unit cell, although that limit is not really set by the code, but it's mostly set by DFT calculations that we use as input. After computing the interactions, Perturbo can compute 2 main types of properties. One is transport properties, such as conductivity, mobility, magnetotransport, as a function of temperature doping. The other set of calculations focuses on non-equilibrium dynamics, including also in the presence of external fields. These calculations can now be done on a wide range of materials, including those with spin collinear texture, so basically ferromagnetism, for example, as well as systems with spin-orbit coupling and anharmonic phonons. So that includes a wide range of metals, semiconductors, oxides, and quantum materials of current interest. So the code is interfaced for the DFT calculations with Quantum Espresso, the most recent version, 7.2. We support a range of pseudopotentials. And in general, thanks to the continued and generous support of the National Science Foundation, we've been able to make Perturbo into a very sharp and efficient tool. For example, if you were to visit our website, you'll see that there's a range of tutorials. There's a full manual to the code. There's also a user forum where people can ask questions. And more recently, we have developed a full test suite and also tools for post-processing that will be covered in the next talk, in particular this Perturbo-code tool. Now, the two guiding principles to develop this code, one is to make it user-friendly, and basically all these tools speak to that. And the second is to make it modular so that people can easily add new types of calculations or new pieces of physics without really knowing the entire code. For example, we had many students who, over the summer, in 10 weeks, were able to develop new tools without really having time to get to know the entire code. Now, that modular design is also accompanied by efficiency. In particular, Perturbo is parallelized with both NPI and OpenMP. We're also developing GPU acceleration. You see here, these are tests done on Cori NERSC's supercomputer, where basically there is a nearly ideal scaling of Perturbo's performance up to about 500,000 of CPU cores. Basically, the code can already be used on large supercomputers. In fact, on NERSC's machine, it is available as a module. The code also provides a unique set of capabilities. Now, there's a growing number of codes focusing on Electron-Phonon calculations, but some of the workflows described here, for example, transport at high fields or Magnetotransport or Nonequilibrium dynamics, the Boltzmann integration framework. These types of calculations done from first principles, basically Perturbo is the only code that currently provides these capabilities. So in general, we've been thrilled by the community response. We released the code in 2021, and in about 2 years, we now have about 700 users, and the paper has been cited over 150 times. And so this basically motivates us to continue with this project and continue growing it and training new users. Okay, now taking a step back, the scientific motivation for developing this code is basically the it covers the focus of our scientific interests in the group. We focus on computing electron interactions and dynamics from first principles. For those of you who are not familiar with that, that means that calculations take the atomic positions as the only input, and using only numerical quantum mechanics without empirical parameters. The goal is to make quantitatively accurate predictions of a range of materials properties. So one of our primary focuses is accurately computing the interactions among electrons, phonons, and other degrees of freedom materials. And with these interactions, we study various dynamical phenomena. One of them is charge transport, where one of the goals is accurately predicting macroscopic transport properties, such as the conductivity and the mobility in the presence of electric and or magnetic fields, but also to understand the underlying microscopic scattering mechanisms that govern these properties and the various transport regimes possible in different materials. Another motivation is studying materials that get excited out of equilibrium, for example, with a light pulse. And here, one of the goals is studying the resulting ultrafast dynamics of the excited electrons, which typically occurs on a femtosecond time scale, and the subsequent dynamics of the excited lattice. And so here, some of the goals are computing the timescales for these processes, the mechanisms, and also predict the associated time domain spectroscopies. So I will show examples primarily of this work, although more recently we have repurposed some of these tools to also study spin dynamics. This is kind of a more recent effort that we'll cover only briefly. Basically, in this context, one can compute spin relaxation mechanisms with the goal of contributing to new fields like spintronics or spin qubits and so on. And finally, and that's the reason we're here, another effort of our group is developing Perturbo to share these novel and accurate first principles tools with the community in the hope that our efforts to develop these methods then ultimately get amplified and enable people to hopefully do interesting new science. Okay, so let me start with one of the key interactions computed in Perturbo. That's the interactions between the electrons and phonons. The idea is quite simple. As the atoms move due to their thermal motion, they perturb the periodic potential seen by the electron. And this perturbation term, if you take it to a lowest order theory, and you second quantize the small displacements, you obtain this linear or lowest order electron-phonon Hamiltonian on a block basis. What this Hamiltonian studies is processes where an electron gets scattered from an initial band state in a given band n with crystal momentum k into a final electronic state by absorbing or emitting one phonon with a wave vector q that accounts for momentum and energy conservation and a certain mode index mode. So this would be acoustic or optical mode. It could be transverse or longitudinal. Now, one of the key quantities of interest is the probability amplitude for each such scattering process. And those probability amplitudes are encoded in these electron-phonon coupling matrix elements. Now, using first principles techniques, as I will describe momentarily, we can compute these matrix elements and resolve them for different electronic states and phonon modes. And it's a significant advance compared to the conventional theory, which, for example, is covered in standard textbooks like Mahan, where you have to make certain assumptions of which phonon mode is, couples with the electrons, or some of these theories work only for limited sets of electron-phonon wave vectors. So this is more of a more general tool. Now, taking a step back, for those of you who are not familiar with density functional theory, as you may know, this is essentially a mean field method to mainly study bonding and ground state properties in materials, with a good trade-off between computational cost and accuracy. In this context, density functional theory is mainly a tool to obtain approximate single particle electronic states, so basically band structure, and wave functions. Perturbo is interfaced for DFT with the quantum Spectroscopy, which obviously has a very large community, so it's a very mature tool that is still maintained and kind of sits at the state-of-the-art of DFT calculations. Now, to compute electron-phonon coupling, one also needs linear response density function theory, or as it's called sometimes, DFT, which stands for density functional perturbation theory. This is a theory where one can apply a monochromatic perturbation with arbitrary wave vector, and then working in momentum space, one can study the linear response of the charge density and also the self-consistent constant potential. DFT does two things here. One, is from the change in the density, one can compute the dynamical matrices, and therefore the phonon dispersion and the phonon eigenvectors. And then second, as a byproduct of the calculation, one also gets the change in the self-consistent constant potential. And basically, this is the periodic part of that change in potential, which can be computed for arbitrary phonon wave vector Q. So now these quantities shown here in red are basically the main ingredients that one needs to compute these electron-Phonon coupling matrix elements. One of the key challenges, however, is that DFPT is both the tool that makes these calculations possible, but it's also the bottleneck because of its high computational cost. So typically, DFPT for solids is only possible for systems, let's say, up to about 50 to 100 atoms in the unit cell, and also typically for moderate Q-point grid densities of about up to, say, 10 by 10 by 10 or so. One of the challenges for computing transport is that we need these interactions on significantly finer grids to capture the scattering processes between various bands and electronic states. So the workflow that is now established to do these calculations is that one starts from DFT and DFPT done on relatively coarse grids, for example, 10 by 10, 10 for both the electron and the phonon momenta. And then one interpolates these quantities to much finer grids, at least 100 cubed or more wave vectors. And this interpolation is done by first transforming this quantity into a localized basis set, typically 1E functions. The idea here is that if you remove any long-range component, which we will discuss momentarily, the remaining short-range part in this localized basis essentially accounts for the hopping between two localized states that is mediated by a perturbation potential at a third site. And so, because it is short-ranged, it behaves rapidly with both of these distances. And therefore, one can do a double Fourier transform of this quantity to interpolate to arbitrarily fine grids and then add back any long-range components, which is due to specific phonon nodes. Once we have these interactions on very fine grids, these are basically very large matrices. They have billions of entries. And one can use this large data set to compute transport and non-equilibrium dynamics. And so computing these matrix elements, interpolating them, handling them, and computing transport and dynamics, these are basically the tools that are carried out efficiently by Perturbo. Just to give you an idea, calculations that are now straightforward and that will be covered as tutorial examples in this workshop are computing the resistivity or mobility for a simple metal semiconductor, or studying electron relaxation in a simple semiconductor. So when I started this work as a postdoc about a decade ago, these were basically open research problems in terms of completing these calculations from first principles. So fast forward to a decade later, now there's been significant progress, both in the methods and the code. And now these examples are straightforward. Basically, the field is in a different place where, as I will show toward the end of the talk, we're trying to develop much more challenging and tools and tackling more challenging problems. As I've mentioned, some phonon modes induce long-range electric fields. And so the electron-phonon coupling is typically apportioned into a short-range part and a long-range part, which is made up by a dipole term and a quadrupole term. The dipole is the well-known Frolic interaction that is due to longitudinal optical phonons. So if you have a polar material where you have a net charge of on the atoms, the longitudinal optical nodes basically behave like a vibrating dipole. Therefore, it emits an electric field. And so the trend of the coupling for this interaction is it goes like the inverse of the phonon wave vector Q. This interaction can now be computed from first principles, in particular using Born charges from linear response DFT. Once we have this interaction, for example, we have shown that for polar materials like gallium arsenide, one can compute transport properties such as the mobility is a function of temperature with a high accuracy. This is an older paper from several years ago. And with a similar accuracy, one can predict microscopic relaxation times of the electrons. For example, you see here that the experimental value for an electron to emit an Electron-Phonon is 165 femtoseconds, and basically the predicted value is within 1%. More recently, we have completed the theory to also show how to compute the quadruple term. So this is a term that goes like a constant at small phonon wave vector. It's in principle present in all systems, but it's particularly important in piezoelectric materials because these dynamical quadruples are linked to the piezoelectric constant. So these are basically systems that are polar and non-centrosymmetric. A typical example is lead titanium, where you see here, if you use direct PFPT calculation as a benchmark, you see that if you don't include the quadruple term, so that's the blue line, then there are very large errors for the electron-phonon coupling for the acoustic modes. And then if you include the quadruple term, then one can accurately predict the coupling also for the acoustic modes. So this kind of completes the theory. And now with these interactions in hand, one can study various processes. As I mentioned, one of them is transport, where we're going to build these scattering mechanisms and so on. The basic theory, which will be covered in more detail later, is in the currently released version, we focus on the Boltzmann equation, which is basically a semi-classical tool where one computes the scattering rates using quantum mechanics, and the dynamics is semi-classical. We also have in our private repository, and as we've shown in a recent paper, we can also do Green-Kupo calculation, which are fully quantum mechanics, fully quantum mechanical, but that we will release in future versions. So for the Boltzmann equation, the idea is if we have the electron-phonon coupling, we can compute the scattering rate and its inverse, the relaxation time, which is basically the time scale for the scattering processes. And from that, using the Boltzmann equation, we can compute the conductivity and mobility within the relaxation time approximation, or RTA, which uses this relaxation time that includes only scattering from the state going out. And basically, one only needs the band velocities, which are computed from DFT and interpolated using quantum functions, and these first principles relaxation times as a function of temperature. However, a more complete approach is fully solving the Boltzmann equation. In that case, one also includes backscattering into the state. One can write this equation as a self-consistent equation for the mean-free path. So it's the product of the relaxation time and the velocity. And so here you see that the RTA relaxation time, which is tau times d, is stressed by the backscattering. And so at self-consistency, one obtains a modified relaxation time, also known as transport relaxation time. And then one can compute the conductivity and mobility, also including backscattering effects. As will be shown later, these two quantities are often similar, but there's cases, particularly for polar materials, where fully solving the Boltzmann equation makes a significant difference. Over the years, we have used these tools to study a wide range of systems that range from simple inorganic semiconductors like gallium arsenide or gallium nitride to organic semiconductors with tens of atoms in the unit cell. We've recently shown a calculation of pentacene that has more than 100 atoms. One can also study various oxides and chalcogenides, including materials with structural phase transitions, and as well as metals, both simple, like copper, gold, and silver, or more complex metals. This type of theory, the Boltzmann equation, essentially works whenever the electron-phonon coupling is weak, and whenever the electrons are not strongly correlated. In these cases, or whenever the spin texture is important, then basically one needs extensions to the theory. So what I've described so far were basically the tools that we provided in version 1 of the code in 2021. Last year, we have released version 2, which also provides a wider range of tools to address, for example, anharmonic phonons, spin-orbit coupling, transport in the presence of magnetic fields, and scattering with defects. So I will describe them briefly. So several systems like oxides and perovskites have structural phase transitions. Typical example is a cubic perovskite, like strontium titanate, that distorts to a lower symmetry phase. Here, the trigonal phase. And so if one is interested in studying the high temperature phase, because DFPT is a zero temperature method, the phonons become dynamically unstable. So this phase is predicted to be dynamically unstable, and one finds these phonons with imaginary frequencies that are shown here as negative. Then, of course, the electron-phonon coupling cannot be computed straightforwardly for these phonons. The idea is to use tools developed in the community, such as TDEP, which stands for temperature-dependent effective potential. These methods can address phonons at finite temperature by including their entropy contribution. And so in this paper, for example, we have shown how to compute phonons as a function of temperature in this material. And once we have accurate phonons, then we can compute the coupling for all modes, including the soft modes. And when one includes this anharmonic contribution, the Boltzmann equation in this case can accurately predict the temperature dependence of the mobility. You see that if you didn't include the soft modes, one would basically make a large error. Now, this will be discussed later, but TDEP used to be an open source code, but that's no longer the case. So we're currently distributing the latest version of TDEP, but we're also working on interfacing Perturbo to a more novel tool for anharmonic phonon calculations. The acronym for that tool is SHA. That will be discussed briefly in a subsequent talk. Another essential piece of physics, for example, when studying materials with heavier atoms, is spin-orbit coupling. In DFPT and DFT, that can be handled by using fully relativistic pseudopotentials, which include the atomic contributions of spin-orbit coupling in the pseudopotential. And so the electron-phonon perturbation becomes a matrix in spin space, and the wave function becomes a spinor. So the matrix elements can still be computed. However, the challenge is calculations, because of their cost in DFPT, are usually done in the irreducible wedge of the Brillouin zone for the phonon wave vectors. And then the matrix elements are rotated to the entire zone. So in the Perturbo paper, we've shown that we can do this rotation accurately by taking into account SU2 rotations for the spinors. At the time, there was a little bit of a controversy where a different code, for example, did not include these SU2 rotations. And you see that when you do that, one basically makes very large and uncontrolled errors. So you can see here, if you didn't include that particular operation, the result deviates from the direct DFPT result. So now that we can compute electron-phonon interactions with spin-orbit coupling, of course, one can study transport and dynamics in systems with heavy atoms. But there's also, it also enables a different set of calculations to study spin relaxation due to phonons. In particular, one can study, as we've shown in this paper a few years ago, the spin flip events that control spin relaxation times in centrosymmetric materials like silicon. And you see that if one computes the spin flip matrix elements, one can accurately predict the spin relaxation times, beautiful agreement with experiment, as well as uncover some of the underlying mechanisms for spin relaxation. This is a topic where we've done extensive work recently, also extending these methods to different theories that also encompass non-centrosymmetric materials. This particular tool is not yet public, but we plan to release it with the next version of the code. But we've also included magnetic fields in the Boltzmann equation, so now one can compute transport as a function of magnetic fields for weak magnetic fields, so without lambda levels. One of the challenges here is that this term includes the gradient of the electronic occupations in momentum space. So that's computed with a standard derivative. And that allows one, for example, to compute magnetoresistance as well as Hall mobility. So that is the mobility that one would measure in a Hall experiment, which is a common experiment to measure mobilities. And it deviates from the drift mobility, which is obtained from the Boltzmann equation without magnetic field. And so here we have shown, for example, in silicon that we can compute both of these quantities with a high accuracy. So this will enable a wide range of studies and systems where one applies magnetic fields to study transport. And then finally, and this is a tool that so far has been available only as a beta type tool that's basically available upon request to the users, but I believe that today we have fully shared it on the website. We can also compute scattering with defects, where basically the idea, again, is if one uses perturbation theory, in principle, you'd want to have the perturbation potential caused by a defect. So you could set up a supercell calculation in DFT. You take the difference between the potential of the pristine system and the system with the defect. However, the challenge is that if you wanted to directly do that calculation, you need to work with the wave function of the supercell, and it basically becomes prohibitively expensive. So working with my student, or former student, Itelu, in a series of 3 papers, we basically unpacked this entire set of ideas where, first of all, we have developed a method where one only needs to compute the potential in a supercell calculation, but then one only uses the wave function of the unit cell. And so that provides significant speed up and initially make these calculations possible for neutral defects like vacancies. Then one can basically repeat the entire workflow, compute relaxation times due to different types of neutral defects or defect limited transport, which basically governs transport at low temperatures. Then we have extended the workflow to charge defects. These calculations are significantly more challenging, so if one wanted to try them, it is best to contact us and to work with Itelu. But the idea, again, similar to the Electron-Phonon, one needs to first subtract the long-range interaction here from the defect, and then after interpolation, using one-way functions, add it back in momentum space. For example, things that you can do is you can compute transport at very low temperatures, and or you can compute transport as a function of doping. So this is silicon. The calculations that are phonon limited that I've shown so far would basically address this limit here, where the system has very low doping. However, you see that in practical systems where you have doping, the transport properties change rapidly with doping. And basically, we have included in the full Boltzmann equation both the phonon and the defect scattering. And so now one can study how the electron mobility changes with doping. And this is a set of tools that is broadly applicable and different from conventional theories of transport. One never uses the effective mass or makes assumptions about the electronic structure, but basically it can be done for any material, including those with linear band dispersions. So more briefly, I wanted to discuss non-equilibrium dynamics. Basically, again, we're thinking of a system that has been excited with light, and we want to study the femtosecond dynamics of the excited electrons. So the first challenge, again, is obtaining accurate interactions, for which we need quantum mechanics, and so that's something that we have discussed. The idea, again, is that different from empirical models, if one has accurate interactions, one can basically do quantitative studies of these non-equilibrium dynamics, and so get quantitative predictions for timescales, mechanisms, and also time domain spectroscopies. Once we have the interactions, we need to solve kinetic equations. And here, within the first principles landscape, you basically have a wide range of methods. Some focus on the wave function, like time-dependent DFT. Others propagate the Green's function with the density matrix. The choice that we've made is, again, to focus on the Boltzmann equation, which provides a trade-off between cost and accuracy, and also the breadth of physics that one can access. In the public version, one can solve the time-dependent Boltzmann equation, so propagate the electronic populations in time using collisions that are computed from first principles. However, in the future, we will also release similar versions that address the time-dependent dynamics of phonons and accidents. So the starting point for these studies is basically an efficient solver for the real-time electron-Boltzmann transport equation, or RTPT. If you want to propagate in time the electronic populations, and suppressing the band indices here, it can include various collision processes, for example, with the phonons, but we're also developing the ones with other electrons. But one of the challenges is that this collision integral itself depends on the electronic populations. And so this basically becomes a large set of integral differential equations. And in this 2017 paper, we basically developed a brute force algorithm that just uses Runge-Kudafort, which is a stable and reliable time propagator. And with a femtosecond or so time step, one can efficiently compute this collision integral at each time step and basically march forward the electronic populations. The idea of this algorithm is basically made efficient by parallelizing the scattering processes, which are distributed first among NPI processes, and then within each NPI process, one uses OpenNP to efficiently sum this integral and then propagate in time the electronic population. So these are calculations that are typically done in dense grids, and so that's where much of the computational cost comes from. Just to give you an example, you can study the dynamics of excited electrons in semiconductors. Here in gallium nitride, where, for example, if you excited electrons in holes with a similar energy offset from the valence and conduction band edges, you see that we found is that the holes relax much faster, about 5 times faster than the electrons, which kind of cool more slowly. And we have shown that this slow cooling of the electrons is also linked to energy loss processes in optoelectronic devices. Recently, this prediction has been confirmed by an experimental group that has measured the transient absorption, so how optical absorption changes in time after one excites the material. But the beauty of these methods is that from the real-time Boltzmann equation, we have access to both the electron and the hole populations. And so not only can you compute and simulate the transient absorption spectrum, but you can also detangle or separate the contributions from the two carriers. So, for example, the results of these calculations are summarized with this line, and we're able to attribute this main signal with a slower time scale of a couple hundred femtoseconds to the slow cooling of the electrons. And also predict that holes, on the other hand, cool much faster, and they're responsible for this shoulder seen at short times. So again, this is just to show an example of how these calculations can predict this ultrafast dynamics and also the associated spectroscopies. You can trust these results quantitatively, which is different from many models to study non-equilibrium dynamics, because, for example, if you took the same interactions in gallium nitride and you use them to compute the mobility entirely from first principles, you see that the computed value matches the sample with the highest purity, with the highest mobility. And using these reliable interactions is challenging in general, but here you can basically go back and validate these calculations. I think I'm running a little bit behind, but I'll just show an example of a feature that was released in version 2 of Perturbo. When now, in addition to the collision integral, we can also add an external electric field, which comes in the form of an advection term. So here, one needs to use different predictor corrector solvers. This will be addressed by Maliev, who has led this work. But what you can do in these simulations is you can progressively increase the electric field. Each time you reach a new steady state where the electrons are kicked up in energy, they basically populate higher valleys in gallium arsenide. And each time one reaches a new steady state where the electron velocity increases. And so in one shot, you can basically track the entire velocity field curve, which is kind of a holy grail in the old Monte Carlo simulations. This is an example here for silicon. You see one can compute the velocity field curve in different direction in very good agreement with experimental data. And so this is a tool that can be applied broadly to power electronics, oxides, and various materials of interest in that context. So finally, this is not the entire story. We have many things planned for the future. Basically, what we are currently working on and things that we have papers on over the last 2 to 3 years are capabilities that we plan to release in the future. In particular, we're working intensely on addressing strong electron-Phonon coupling, so basically going beyond perturbation theory and systems that include polarons. These are some recent papers on this topic from our book. Or materials that include strong electron coefficients, where density functional theory fails, and one needs to use things like Hubbard U extension of DFT or dynamical neutral theory. And also spin relaxation with broader tools than the simple spin flip calculation that I've shown. So we anticipate that these methods will contribute to future studies of a wide range of quantum materials. And finally, on the software frontier, we've also embraced the data-driven / machine learning methods. And so we've developed tools in several forthcoming papers that make these calculations significantly more efficient by using data-driven methods. For the ultrafast dynamics, we've similarly made progress, and there are tools that we plan to release in the future to study dynamics in the presence of accidents. So where you cannot separate the dynamics of the electron hole carriers, but rather to study the dynamics of the bound electron hole pairs, and also the associated ultrafast spectroscopies like photoluminescence or fine domain ARPIS to study these processes. And you can read these papers to learn more about this, but also study the time-dependent dynamics of the phonons, which were frozen in the calculations that I've shown, the ones that are in the current version of the code. And finally, here we're also developing data-driven methods to accelerate these simulations. So in summary, this is basically a very versatile tool that initially was meant to focus on electron-phonon interactions, but now it has become a broader set of tools and basically bigger project that will continue to grow in the future. The idea again is to provide a code with a gentle learning curve. I hope that will be the experience during this workshop, where if one has a new idea that is not something that is not implemented in the code, one could easily try to add it. The idea is also to have a tool that can address wide classes of materials where one could have different challenges, from strong coupling to correlations, non-trivial spin, Anharmonic phonons, and so on. I've highlighted some of the features that we have released in the last version. So we had a workshop for Perturbo 2 years ago. And basically, these are features that we did not have back then and that will be described extensively in this workshop, as well as new tools, particularly Perturbo-5, which will be described in the next talk, that enables very efficient post-processing of the calculations. And so I believe that the future is very promising for these tools, and we're encouraged by the community response. And so we plan to focus on strong coupling, polarons, correlated systems, spin dynamics, data-driven methods, and GPU parallelization, among other features for future versions of the code. Okay, I will end here, and I'll be happy to take any questions.